Hi, I'm Maya Steiber, a fourth-year PhD student from Johns Hopkins University's Intuitive Computing Lab. I'm interested in shaping how we collaborate with robots and in what tasks we're willing to have that collaboration by understanding and using humans' multimodal responses to robot errors to promote effective human-robot teaming. Today I will tell you about a project that will demonstrate that we can detect errors within reasonable accuracy and timeliness using social signals, and that this method can be generalized to different tasks and to different types of errors. In addition, this approach is task, error, and person independent. We are in the middle of a major shift in society where we're going to increasingly see robots integrated into daily life. As a result, robots will be collaborating with humans either directly or indirectly, and this collaboration will augment human capabilities. The foundation of these teams will be trust. These robots will certainly make errors. Besides the direct impact errors have on safety and task performance, these errors will erode user trust. As a result, people will be less willing to work with robots. However, if we can reliably identify errors in a timely manner, we are able to effectively maintain that trust, mitigate the error's effects, and recover from them. Current error detection methods are specifically crafted for each particular task and only a small set of predefined errors, and so are not generalizable or adaptable. Unfortunately, errors can happen during any task and don't necessarily fit our expectations. Their effects vary based on the situation and collaborating individuals. Therefore, providing a robot with enough information about the task and user to obtain an accurate model of an error and its impact is difficult. However, as I mentioned, robot errors are unexpected, and it's that unexpectedness that will likely elicit natural human responses, social signals, from their human collaborators. Through these social signals, humans can reflexively and implicitly impart information about the error, task, and their own mental model of the robot to the robot. So we focused on leveraging and modeling natural facial reactions to develop a real-time error detection system. The natural facial reactions are robust and universal in response to robot errors, even in non-social tasks with non-social robots. To enable real-time data collection of human response, we created a platform built on Microsoft's platform for situated intelligence. Our system used input from 2 cameras strategically placed to maximize facial detection confidence, regardless of the participant's position, allowing for the participants to have full freedom of movement. The system then synchronizes the video streams, calculates the AUs per stream, and selects the AUs from the more confident facial detection and logs them. In addition, the system allows for integration of an error detection algorithm to run in real time. Our data collection study was contextualized in a programming by demonstration scenario in which participants provided task demonstrations through kinesthetic teaching, allowing participants to be treated as the task experts, which is similar to real-world applications. In actuality, their robot's training had no effect on the robot's behavior as its movements were pre-programmed by the experimenter. The actual task was having the robot unpack 2 boxes from a crate and place them on a table. The robot places the first box without error, and then for the second box's picks in place, we inserted a pre-programmed error. After we collected data, the AU intensities are the input into a AU modeling algorithm. We fed in each time step into a classifier to determine if that time step is an error. Because errors happen over a period of time, we use a sliding window to filter out spurious error classifications. If enough time steps are above a threshold, then the algorithm outputs estimated error start as the earliest time step in the window that was classified as an error, and the detected error time step as the newest time step of the latest error classification. We quantified how fast participants generally reacted to robot errors. On average, they react within a second of perceived error start, which is timely within this timescale of human perception. This shows us that by using AUs, we do not lose any noticeable time, quote-unquote, waiting for the user to respond. In addition, the algorithm's performance in terms of algorithmic detection delay, which is the root mean squared error of the time between algorithmic error detection and the start of the error, was fast in relation to the time it would take to mitigate an error. You can read our paper for more detailed results. To explore how well our method for real-time error detection generalized to different tasks and error types, we ran a case study evaluating our algorithm against different tasks and errors than the data collection study. We contextualized our case study in a programming by demonstration sorting task. Each participant experienced 3 different types of errors. There was generalization errors, physical errors, and conceptual errors. We integrated the error detection algorithm, which was only trained on the data from the data collection study, into the data collection system I mentioned previously, so to allow for the robot error detection based on human reaction in real time. The result from our case study shows that the algorithm is able to generalize to other tasks and errors. Here is an example trial. The image shows the progression of reaction to an error and the outputs of the detection algorithm. What is interesting about this case is that the participant noticed the gradual deviation of the robot's path due to an error and started reacting before the coder indicated the error had started. So as a result, the algorithm had the ability to take advantage of that early reaction and detect that the robot is making a mistake before perceived error start. From this study, our findings show that we are able to detect and temporally localize within a reasonable accuracy and timeliness using AUs, and that this algorithm can be generalized to a different task and to different types of errors. In addition, this approach is task, error, and person independent. This work is the first step towards generalizable, robust error detection, which is key to successful error mitigation. Thank you.